Welcome back to our academy. In last video we have started our new subject, that is vibration. In last video we have seen introduction of vibration, in which what is vibration, what are its effects, that is good effects, bad effects, how to remove vibrations, and what are the elements of vibrating system we have discussed. In this video we will discuss about types of vibration. Also we are going to prove vibration as a simple harmonic motion, that is SHM, and we will see vector representation of vibration. Let's start. So types of vibration. First type of vibration is free and forced vibration. What is meant by free vibration? If external source is present while vibrating system, then it is called as a forced vibration. Okay. If there is no any external source or external source is absent, then vibration is called free vibration. That means if we move body from its equilibrium position and release and allowed to move or allowed to vibrate its own, then it is called as free vibration. And instead of that, if we are continuously pulsating that system, then the vibrations are called as forced vibration. In case of free vibration, body will vibrate with its natural frequency or system is vibrated with its natural frequency. In case of forced vibration, system will vibrate with its forced frequency. Okay. Then next type is damped and undamped vibrations. We have seen in last video that damper is element which absorbs energy and makes system to rest. If there is a damping element present, then vibration is called as damped vibration. And if damping element is absent, vibration is called as a undamped vibrations. Okay. Then next classification is according to motion. It is longitudinal vibration, transverse vibration, and torsional vibration. In case of longitudinal vibration, see here, if this is a system, here in this system, this is the shaft and this is the axis of this shaft. If body vibrates or moves along this axis, then vibrations are called as longitudinal vibrations. Okay. In case of transverse, again this is the system, shaft and mass. If here body is vibrate transverse to this axis, it means in this direction, then vibrations are called as transverse vibration. Okay. In case of torsional, suppose again same diagram, but here if rod gets twisted this and this direction alternatively, then that means clockwise, anti-clockwise directions, then vibrations are called as torsional vibrations. Okay. Next important type is linear and non-linear vibrations. Okay. The vibrations which are governed by linear differential equations are called as a linear vibrations. And the vibrations which are governed by non-linear differential equations are called as non-linear vibrations. Okay. So next type is steady and transient vibration. Okay. Here what is meant by steady vibration? If amplitude of vibration remains constant throughout its life, then system is called as, or vibrations are called as steady vibrations. Then transient If amplitude changes with time, then systems are called as transient. Okay, transient vibrations. The next important is single degree, multi-degree systems. Okay, suppose this system, okay, it consists of string and mass. If you pull this or move this mass from its equilibrium position, it will start move or perform transverse vibrations. Now, at any instant, to specify condition or situation of system, we have to only require to specify only this theta value. That means single parameter is sufficient to specify condition of system at any instant. Then vibrations are called as single degree vibrations. Okay, instead of this single mass, if we have two masses m1 m2 here, and if we deflect this system by some amount, say theta, then at any instant we require to specify this theta 1 and this theta 2 to get complete understanding of condition of system. That means it comes 2 degree system, and if we add more masses, then we require more number of independent parameters. Then the system is called as multi-degree system. This is for pendulum. In spring also, if there is a single mass, we have to specify only single displacement, it is x. Okay, if there are two springs, then we have to specify two displacements of two springs at an instant, then that will become double degree or multi-degree system. Then next type is, this is important type. Okay. Then next type is deterministic and random vibrations. Deterministic vibrations means if magnitude of external vibration, external excitation is known to us, then it's called as a deterministic vibration. And if magnitude of external excitation is unknown to us, then vibrations are called as random vibrations. Okay. Next important type is harmonic and non-harmonic vibrations. Okay, harmonic means external excitation force is periodic and sinusoidal, then vibrations are called as harmonic vibrations. Then if external excitations are periodic but not sinusoidal, then vibrations are called as non-harmonic vibrations. So these are some important types or classifications of vibrations. Now next point is in this point we are going to prove that vibration is a simple harmonic motion. Okay, consider we have a spring which is having initial length del. Okay, it is freely hung from support. Now when we add some mass to this system, then it will deflect by some amount due to weight of that mass. Okay, now with m is the mass, del is the initial displacement or initial length, delta is the static displacement of this system, k is a spring constant or force per unit, resisting force per unit displacement. Okay, or spring stiffness. Then when we add mass, then at equilibrium upward spring force, okay, is equal to downward weight force or downward weight. Downward weight is nothing but on multiplication of m into g, that is acceleration due to gravity, and upward force is k delta st. Minus sign indicates both directions are in opposite sense. K is a spring constant, that is resisting force per unit deformation. Here deformation is a delta st, so spring force is k into deformation delta st is in opposite direction of mg. Now if we pull this mass by some amount, say x, and release, okay, then when we pull this mass, then spring force, due to spring force, spring is trying to pull this mass in this upward direction or equilibrium direction, and when we release this mass, then due to spring force or restoring force, mass will trying to move in upward direction. But as we kept, or when we move this mass in downward direction, we are placing or giving accelerating force in this downward direction. Then at any instant we have accelerating force acting in downward direction is equal to restoring force acting in upward direction. So accelerating force here first is due to weight of that mass, which is mg, and m into x double dot, it is m into a, acceleration, it is accelerating force, mass into acceleration, is equal to restoring force is, now here if deformation is, this deformation is x, then total deformation in system is x plus delta st. So spring force in upward direction is minus k into x plus delta st. Okay, now from equation 1 we know that mg is equal to minus k delta st. So cancelling both these terms, we get m x double dot is equal to minus k into x. So x double dot is equal to minus k m into x. That means here x double dot represents acceleration, k is constant for given spring, m is constant for given system. So here acceleration is proportional to displacement and is in opposite direction. Okay, that means this, hence this system is in SHM because this satisfies this condition of SHM. Acceleration is proportional to displacement and directed away from displacement, that is towards center. So this motion, this as acceleration is proportional to displacement but in opposite direction of displacement, so this motion is SHM, this vibrations are in SHM, simple harmonic motion. Okay. Now next is a vector representation of this SHM motion of vibration. Consider x is the amplitude of displacement, then x is the amplitude of system, omega is the angular velocity, then at any instant displacement in SHM is given by x at any instant t is x sine omega t. Okay. Now velocity is nothing but dx upon dt. Okay. Then taking derivative we get x omega cos omega t. Okay. Now next is for cos omega t we can put is equal to sine omega t plus pi by 2. So velocity becomes x omega sine omega t plus pi by 2. Now for acceleration we take differentiation of this velocity vector, then it becomes x omega cos omega t plus pi by 2. Sorry, if you take derivative of this, here I have to take derivative of this because both represents velocity here. So acceleration becomes x omega square, sine, derivative of sine is cos omega t plus pi by 2 and is equal to minus x omega square sine omega t. Cos omega t plus pi by 2 is, or cos pi by 2 plus theta is minus sine theta. So replacing cos by sine. So these are the values of displacement, velocity and acceleration. Now to represent on vector plot, let's consider two axes. Okay, this is the origin. Now amplitude is x, amplitude of displacement is x. Let's take this is the amplitude. This length represents amplitude x. Now vector is moving with angular velocity omega. Then at an instant t, angular displacement will be omega t. Okay, now we want to represent x sine omega t. So sine is nothing but opposite side. So this height is x sine omega t. That is nothing but displacement vector in vibration. This vertical height is displacement vector. Then next is velocity vector is equal to its amplitude is x omega, and into angle is sine omega t plus pi by 2. This angle is omega t. Add pi by 2 here to this, and this amplitude is capital X omega. Then sine of omega t plus pi by 2, it will be this height. This height will be x omega sine of omega t plus pi by 2. It is nothing but our velocity vector. Okay, in this direction, here in this direction. Last is acceleration vector. It is along omega t direction. Negative sign indicates opposite direction, so opposite to our displacement. Having amplitude is x omega square. This vector represents acceleration at any instant with x omega square sine of omega t, and minus in negative direction. These are the vector representations of displacement, velocity, and acceleration at any instant. So in this video we have seen classifications of vibrations. Second, we have proved or shown vibration as the SHM, and lastly we have seen vector representations of vibrations. In next video we will see analysis or methods of analysis of vibrations. If you like this video, please subscribe our channel and like this video. Thank you.